Hi everyone, this is Advanced Statistics for the Social Sciences. In this lecture, I'll begin reviewing some of the topics covered in your introductory statistics courses that will serve as the foundation for the concepts we discuss in this class. Before we begin, we should discuss some basic definitions that we'll use throughout the course. These are especially important for working with datasets to know the correct terminology of the components of a dataset. We define individuals, or cases, as the objects or events described by the data. These could be people, states, rats, or other things. We define variables as the measured characteristics of each individual. Essentially, in our studies, variables are anything that can take on different values or amounts. Some person variables would be things like age, education, attitudes, or blood pressure. State-level variables could be things like landmass, unemployment rate, or region. Some rat variables could be things like weight, brain size, or the time it takes to get through a maze. We define raw data, or scores, as the data representing any individual. They are exactly as collected prior to statistical analysis. Exactly as collected means that we have done no transformations on the data. For example, we haven't calculated any z-scores. So using these definitions, for example, if I am an individual or case in a study of people, I will have a score on each variable measured. I am a case, and let's say the variables measured are height and eye color. My score on height is 67 inches. My score on the variable eye color would be brown. We also distinguish between values and scores in a dataset. When I use the term value, I mean the potential values of a variable. Values refer to the quantities or labels that are the options for a particular variable. When I use the term score, I mean an individual's data point or raw data on a variable. So, let's say the variable that we're measuring is how much you agree with a particular statement, such as, I like sushi. The potential options or values range from strongly disagree to strongly agree. I choose strongly agree. Thus, my score for this variable is strongly agree, or a score of 5 on the scale in the picture. Your score could be different. Another important distinction for the statistics I'll be talking about is the difference between population and sample notation. We are going to differentiate between sample and population statistics. Sample statistics are represented as lowercase letters with a bar. Population statistics are represented as either Greek letters or uppercase letters with a bar. We are also going to differentiate for the number of scores. The sample number is lowercase n, and the population number is uppercase N. Our sample will differ from the population. A sample estimate is just an estimate of the population parameter. So because sample estimates and population values or parameters differ, we try to distinguish between numbers that come from the sample or population distribution using notation. Now let's begin our review. I will start by reviewing commonly used descriptive statistics. Descriptive statistics are statistical tools used to organize, illustrate, or describe the basic features of data. Descriptive analyses are used to summarize existing data, display data, communicate data, and distill data down to its important features. Descriptive statistics don't tell you everything you need to know, but they are an easy way to summarize a lot of information. A summary is a brief statement of the main points of something. The purpose of a summary often is to make it easier for us to process. Descriptive statistics are like summaries of a larger set of data. When I see a descriptive statistic, it helps me understand and process the data quickly. Here are some examples of descriptive statistics that give us a quick summary of large sets of data. For example, 9.5% of people in the US are left-handed. Below, you'll see that a distribution of the Stranger Things Season 1 ratings on Metacritic. These are both summaries of a much larger set of data. Describing a sample of data often begins with organizing the data into a table. A frequency table is one way to organize your sample's data on a variable. This frequency table has the numeric values of scores in the data along with their frequency. It is good practice to include frequencies of 0 in your table along with their values so that you don't accidentally truncate the range of the data. So in this table, for example, you can see the purple arrow is pointing to a 0. This is indicating that I have included potential values within the range of data, including their frequency of 0, so that we know that all of those values were measured. While frequency distributions are visually descriptive, measures of central tendency are numeric descriptive statistics. When data are collected on a variable, scores generally take on a range of values and tend to be clustered around the middle or the center of the range. The three measures of central tendency are the mean, the median, and the mode. The mean formula is shown here. It's the sum of the scores divided by the total number of scores there were in a sample. The median is the point on the score distribution, separating the cases scores into two equal parts. The mode is the most frequently occurring value or values in a distribution. There can be more than one mode if several values in a distribution are commonly observed. Measures of variability are also numeric descriptive statistics that tell us how scores differ from one another. Measures of variability indicate the spread of the distribution. The three common measures of variability are the range, standard deviation, and variance. For the range, we simply subtract the lowest score in the distribution from the highest score in the distribution, and that gives us the interval containing all the data. The formulas for the standard deviation and variance are shown here. The standard deviation is the average distance from the mean, and the variance is that average distance squared. In order to understand the next descriptive, it's important to know the characteristics of the normal distribution. I'll cover three important characteristics of the normal distribution. The first is that if a frequency distribution is unimodal, it has just one highest point. That means that there is one mode. So here, the normal distribution is unimodal. It has just one highest point, or one mode. Part of this characteristic also is that the mean and the median are equal to the mode. A second characteristic of the normal distribution is that the curve is symmetrical with respect to the mean, median, and mode. This means the right half is the same as the left half. If you folded the distribution at the mean, the sides would be mirror images. The third characteristic is that the normal distribution is unbounded, meaning the normal curve tails extend indefinitely in both directions, approaching but never touching the horizontal axis. This means the tails go from negative to positive infinity. They approach the x-axis, but they don't touch it. The normal distribution is a probability distribution, and because it is, the total area under the curve is equal to 1. The distribution is completely described by the mean and the standard deviation. That is, the mean and the standard deviation characterize the shape and location of the normal distribution. Using the normal distribution, we can compute the probability of score occurrence for any range of values. The empirical rule of the normal distribution states that for a normal distribution of scores, 99.7% of the data fall within 3 standard deviations above or below the mean. Remember that real distributions of data have different means and standard deviations than the normal distribution. Z-scores are standard scores that allow us to make comparisons between the scores in our distribution of data to the normal distribution. A z-score is calculated for every score in the dataset and is the difference between that score and the mean of scores divided by the standard deviation. Z-scores help us map our distribution of scores onto the standard normal distribution. Our distribution will have a mean of 0 and a standard deviation of 1, just like the normal distribution, once we convert our data to z-scores. Look at the z-score of positive 1. It's located 1 standard deviation above the mean. Then, after we calculate z-scores, we can use a z-table to figure out the area under the curve, or equivalently, the probability of score occurrence. So let's tie together the information from this review. A frequency distribution is an observed distribution of scores. We can use an observed distribution's central tendency, or mean, and variability, or standard deviation, to standardize it with z-scores. When we do this, we can use probabilities to compare our distribution to the standard normal distribution and determine the likelihood of scores occurring in a given part of the normal distribution. This concludes the first lecture of Review Statistics. In the next lecture, I'll review basic inferential statistics and introduce the concept of modeling data.